Unlike the other models, in our infection models, we'll see state transition across more than two states. It's not just flipping from one to the other states. We're going to see 3 states, for example, and there are variants with even more, 4 or 5 states. And also, instead of looking at discrete time, we look at continuous time through the more convenient mathematical representation of differential equation. We will first look at the population-based infection models, which should have been brought up in the last lecture because it doesn't involve topology. And then in the next segment of the video, and the last one of this lecture before the advanced material part, we'll look at the topology's impact together with a case study. So the state transition diagrams can be visualized as follows. We'll talk about 3 variants of the infection model, starting with the simplest one. S stands for susceptible, I stands for infected, and R stands for recovered population. Okay. We'll be looking at also the percentage of the overall population rather than absolute values. And in the state transition diagram, we see that if you are susceptible to an infection disease, this is where the infection model started originally, thus these particular choice of words, you have a chance of being infected. And the rate of that happening is represented by a beta. And if you are infected, then we have a choice of deciding what to say in the model. One model, the simpler one, says that then you just stay infected forever. Another model says, well, you may actually be able to recover or at least go back to susceptible with a certain rate gamma. And the third one says you actually will truly recover and become immunized from this infectious disease with a certain rate gamma. So let's start with the very first model. Just a word of caution that the beta and the gamma rates of transition in these diagrams actually denote slightly different concept. For beta, we're representing the rate of getting an infectious disease that's proportional to the product of the susceptible and infected population. And therefore, the equation we'll write down, the differential equation, is ds at time t dt is minus beta s of t and I of t. Again, s of t and I of t are the susceptible and infected percentage of the population at time t, continuous time, so that we can use differential equation and integration to solve the model. Okay, so the rate of change of s of t is basically minus beta. Why minus beta? Because you are leaving from this susceptible to, well, the worst state, the infected state. Okay? And as I mentioned, that beta is the rate based on the product of how many people are susceptible, how many people are infected in the product form in the assumption of this model. We can, of course, also write down what happens to the I population. The rate of change of that is a positive beta because you're moving into that state, S of t, I of t. Now, 2 obvious observations. First, we normalize the overall population. So at any time, S of t and I of t are sum up to 1 or 100%. And therefore, naturally, ds dt plus di dt is 0. That's why these two are exactly just negative of each other. Second observation is that, as you can visually see already without any algebraic representation, this is going to suck all the population, eventually be 100% infected. Well, that's why this model is too simplistic, but it's a good starting point. And indeed, we can solve this differential equation. And skipping the solution differential equation, which is now the subject of this course, and you can easily verify by differentiating the answer, its correct answer, we have the following result. Okay. The infected population I of t follows the following shape and initialization, I of 0. and exponential growth e to the beta t, okay, and then divided by initialization condition times e to the beta t. And this is what people call a sigmoidal function, in particular represented as a logistic growth. Is actually coming out of a very standard economic modeling of these kind of dynamic systems. And we can plot it on a graph over time t, both S and I. The S population clearly goes down to 0 because it has to add up with I to 1, and the I population started out from some initialization condition very close to 0 all the way up to 100%. Okay. And this is the inflection point below which is concave, above which is convex, above which is concave. Now, we say that model doesn't quite make sense, right? If you are infected, maybe you'll be able to come back to the susceptible state rather than staying in infected state forever. And once you provide this path of state transition with a rate gamma, as you can guess that at equilibrium, as time goes to infinity, you won't have 100% of people in the I state, because there's always some people moving back. You just want to look at equilibrium where moving in and moving back balance each other out. And this moving back is really just people from the infected state being recovered, and therefore it only multiplies I of t, it does not multiply S of t. Okay, it's not just susceptible people coming into contact with infected people. And therefore the overall equation now, the rate of change of susceptible population, has two components. The first term is people coming back in from the infected state, gamma times I, minus people getting infected, which is beta times the product of S and I, because you need susceptible people to come into contact with infected people. Now, of course, you can also write down di of t dt, the rate of change of that, which is really just minus the above expression, because I and S must add up to 100% all the time. Okay. Now, again, skipping the derivation of the differential equation solver, we see that we again have a closed form expression. For example, I of t turns out to be 1 minus gamma over beta, a constant weight in front of this expression is a ratio, c, some constant, okay, that depends on the initial condition, I of 0, S of 0. We just don't care to write them down at this point, because it's the shape and the rate of the growth that we would like to highlight. So now the growth pattern clearly now depends on beta versus gamma. Okay. And we're going to denote this ratio beta over gamma as a sigma. This is so-called a basic reproduction number. Sometimes it's denoted by other symbols with some subtle differences that don't concern us at this point. Okay. A standard, typical trajectory can be visually represented as follows. I'm plotting the S population here over time, and then the infected population. You can see that it turns out in this case it's about 90% infected, 10% remain susceptible as the equilibrium for a particular pair of beta and gammas. Now we'll later come back to this basic reproduction number gamma in the next model. But if you look at this model, you see that if beta is less than gamma, or if the sigma is less than 1, then the infected population will actually go down exponentially, right? Because this exponential will be a negative exponential. Whereas on the other hand, if beta is bigger than gamma, in other words, the sigma is bigger than 1, okay, then we see that the infected curve will go up, but it won't go up to 100% necessarily. So this is the case for this. If I have to plot this case, then the I curve, instead of going up like that, will be going down exponentially. In other words, if you can recover fast enough, then you won't even have a rise in the I population. So now we go to the third, and for us the last infection model of influence. So here, instead of just looking at 2 states, we have 3 states now. Okay, S goes to infected. Once you're infected, then with a certain rate of gamma, you actually can become truly recovered. Not only you're not infected, you're no longer susceptible anymore. You got immunization from this recovery process. And therefore, we have to write down 3 differential equations. This rate is minus bs times I, just as before. The contact of susceptible and infected population with a rate of beta. Then the infected population's rate of change is, you can see visually, beta coming in, but then also gamma going out. That part. And the recovered population's rate of change over time is simply gamma times the infected population time t that's coming in. Now you can try to solve this trio of differential equations. It turns out that we don't have a closed form solution to the resulting equations. But we can observe the following qualitative behaviors. Again, this sigma, basic reproduction number, beta over gamma, plays an important role here. In this particular model is actually sigma times the initial susceptible population percentage S of 0 at the onset of this infection. That plays the threshold levels role. If sigma S of 0 is less than or equal to 1, then infected population actually decreases. Okay. The initial value S times this basic reproduction number is not large enough to cause increase of infected population. That's all good. However, as in all the pandemics, this will be large enough, and then you will see IT infected population going up. Okay. How high does it go? Well, that depends on a few factors, including the initial conditions. Now, S is always a decreasing function. In this numerical plot of a particular example, you see S going down because this is a one-way arrow. Eventually, everybody drinks out of S and moving into recover. So eventually, recovery reaches 100%. But in between, during the transient, before the equilibrium, you see a large spike of this infected population, in this case going to 2/3 of the entire population before it eventually dies down. This is a very typical pandemic infected population, hopefully not as big in terms of absolute scale as this graph shows. Now, of course, we have assumed there's no death or birth. In particular, there's no mortality rate of people in the infected state. For deadly diseases, then people will die out of this. If the mortality rate is, say, 1%, then this means the area under this curve, it's 1%, are the people that will die through this transient stage before eventually people are fully recovered and immunized. So far we have assumed that the impact is on the entire global population. So if somebody is in Europe and you're in South America, you can also get infected. Now, obviously, for certain influence models, such as infectious disease itself, that's hardly realistic. So we have to now take into account the impact of topology.